Hello, today I want us to learn about computer architecture. So we are going to look at mainly the central processing unit, which is also known as the microprocessor. So that is what we are going to look at today, and we are going to look at von Neumann architecture and how it has been able to impact the current microprocessors designs that we are having in both our smartphones and mainstream computers. Now, looking at the central processing unit, the central processing unit is the brain of the computer, is a single microchip that is very important, and it comes in different forms and different size depending on the device that is going to use the CPU. But the execution and matter of data processing and execution of instructions is basically the same. Is basically the same. Is basically follow the order that has been there ever since the CPU were invented. Now the CPU has the responsibility of execution and processing of all instructions in a computer. Now the CPU consists of three main components. We have the control unit, the arithmetic logic unit, and registers together with buses. So most commonly in our learning endeavors and learning processes that we normally encounter as we learn about computer, we only know of central processing unit consisting of control unit, arithmetic logic unit, and memory. But I also want to tell you that memory in computer is basically the registers and the registers that we are using are there, and these registers stores basically the instructions, the command, and also the data that has been processed and that which is being processed. So when you hear registers, don't wonder what exactly is it that we are talking about now, yet you were told or learned about the memory. So the registers are the memories that we have right there within this device. Now, let's briefly look at von Neumann architecture and what it was all about. Now, von Neumann architecture was a design that was invented by John von Neumann in around mid 1940s. Now, prior to this time, the computers were not able to store and access memory content as they are today. As it were, the computers were being fed data on the go. So early computers were fed data while the machines were actually running. So it was not possible for the computers to operate in a way that was optimal in their way, because there was no means of the computer itself having some instructions and data or a way of storing data, and the computer is able to access those data or that data in a manner that will not be influenced by human beings. So in the mid 1940s, John von Neumann developed the concept of stored programs in a computer, which has been the main basis of computer architecture since then. So the features of this invention, or the features which were very critical and proposed and invented by John von Neumann architecture, were as follows: the concept of central processing unit. The central processing unit was able to access memory directly, without having people to feed the computer data. Computer memories could store programs as well as data. Stored programs were made up of instructions which could be executed in a sequential order. So von Neumann design architecture looked something like what I have here for you. The design had the following registers. We had the memory address register, the program counter, we have data memory data register, there was current instruction register, we had the accumulator, we had the system clock, we had the control unit, and arithmetic logic unit. And now those were very important elements that were involved or that are involved in the central processing unit. So normally the instructions of the next the memory location of the next instruction to be executed is normally stored in the program counter and passed to memory address register through the influence of the control unit through the address bus. Then the memory address register will be used to reference the memory location through data bus, and from there the memory address register is going to be referencing the memory location where the data is stored through the address bus. Then once it is been able to identify the memory location, then the data bus will fetch that data from the memory location into data memory register, after which it will be sent to a current instruction register awaiting processing from the control unit, which is basically the controller and the executor of most of the tasks that are going down within the system. So that's how it is. Later on I'm going to help you understand how the execution normally takes place, but that's how this design of the CPU proposed and implemented by John von Neumann was structured and how it worked. Now let's move on to the basic components of the central processing unit. We have the basic components of the central processing unit. So as it is, this is not all about a central processing unit. There is a lot of information, a lot of things to be learned about the central processing unit. What I'm just offering you is just simple understanding of arithmetic logic unit. So if you are interested in this kind of information, you can keep in touch so that you are able to see and learn about such as I'll be able to develop such content going forward, or you can even access many resources that are available online, and you can be able to learn much more on the same. So we are looking at the components of the central processing unit. Now, the main components of the central processing unit, as I mentioned earlier, are the control unit, arithmetic logic unit, and the registers. But also, we also have the system clock, which is very important, as it is the one that is able to make sure that every execution that is being done is in synchrony, and the computer is doing its function in a matter of time and what is expected as far as the speed of execution and precision of execution is concerned. Now we have arithmetic logic unit, which allows the required arithmetic to be performed, or even logic operations to be carried out during the processing of the computer. So during the processing, or when the computer is running, there are arithmetic operations or even logical operations that must be carried. So the logic and the arithmetic operations are normally performed by arithmetic logic unit. So that is in essence what arithmetic logic unit does. Then we have the control unit. Now the control unit reads instruction. Okay, so it reads instruction from the memory, the address of the location where the instruction can be found, or where it is stored in the program counter. This instruction is then interpreted using the fetch, decode, execute cycle, which we're going to look at later on in this series. So during the process, signals are generated along the control buses, or control bus, to tell the other component of the computer what they are supposed to do, or in essence what they are supposed to work upon. So the control unit ensures there is synchrony of data flow and program instruction throughout the computer. So that is the main function of the control unit. There is also the system clock, which is basically used to produce the timing signals for the control bus to ensure synchronization taking place within the computer, and the computer is not crashing. All right. Then the RAMs hold the data and the programs needed to be accessed by the CPU. The RAM is often referred to as immediate access store. So the CPU takes data and programs held in the backing store, right? That is the hard disk, and put them into RAM temporarily. RAM is the workbench of the computer. This is where most of the execution takes place. Okay. So this is done because read and write operations carried out using RAM are considerably faster than read and write that are done by the backing up storage, because you see the hard disk is far away and it's not closer to the processor as compared to RAM. So that's why there's that difference in speed in operations or read and write operation being carried out at a different pace in the RAM and in the hard disk, because of technically the distance between the two, that is between the microprocessor and where exactly data is positioned. Now we have the registers, which are considered memories within the processor, and these registers are fundamentally important in the sense that they are the ones that are able to make sure that the instructions and the memory location and the data is fetched and executed precisely and in a manner that is consistent with the speed of the processor. So one of the most fundamental components of a Neumann system are the registers, which are also normally the general purpose special types of registers or memories that are there within the microprocessor. So we are just going to look at the major registers that are there and their functions. Then later on we are going to look at how the whole thing works. How is the processing taking place? How is the execution taking place within the computer processor during a normal execution of data and instruction? So there are various registers. As you can see, we have current instruction register, we have accumulator, we have memory address register, we have memory data register, then we have the program counter register. So let's start off by looking at the current instruction register, which is normally abbreviated CIR. So it is abbreviated CIR for easy identification, but also it is important to abbreviate them so that when you are drawing the design, you are able to precisely see the components and how they operate. So this register stores the current instruction being decoded and executed. So that is the work. So the instruction that is being decoded and executed is normally stored in the current instruction register. Then we have the accumulator, which is a very important piece of register that normally stores data or is when carrying out calculations or even store data temporarily during calculation. So that is the work of accumulator. Then we have the memory address register, which normally stores the address or the current location of the data being read from or written to. Okay. Then we have the memory data register, or sometimes just called buffer register. So this register stores data which has just been read from the memory, or data which is about to be written to the memory. Okay. Then we have the program counter. So this one stores the address where the next instruction is supposed to be found. So those are the registers as they are now. We just to remind you a bit, we have the current instruction register or CIR, then we have accumulator, then we have the memory address register, then we also have memory data registers or simply buffer register, and finally we have what we call the accumulator. We have what we call the program counter. So that is it. So the next thing I want us to look at the bus, the system buses and the memory and how they work in synchrony to actualize the purpose of the central processing unit. So this is how the individual devices are organized. So as you can see, we have the CPU. There we have the memory, we have the input output ports, and so we have the three types of buses. We have control bus, address bus, and data bus. So this is how the the buses and the memory locations have been connected, and as you can see, we have the data bus is represented by the green arrow. So as you can see, the green arrow has both arrows on both ends, meaning that it is bidirectional. Then we also have the violet color representing the address bus, which is also unidirectional. As you can see, it only points from the CPU to input and output device there. Then we have the control bus, which is normally bidirectional. It can be sent in either direction or in all the direction if there is something like that. But then that's how the bus system is organized within the computer there. Then we have the computer memory is made up of a number of partitions, as you can see. Then these memories, they have got each partition consists of an address and its content. So we have a table here. Okay, let me see whether I can be able to reduce the so we have this table here, the table 3.2, which tells you or gives you memory location, their numbers, and technically the content that they constitute, or the information they are in the addresses that have been stipulated on this table. In real computer memory, the address and its content are actually much larger than this. So this is just an example. As I mentioned earlier, this is just I'm just giving you basic understanding. So this is not that this is the only information and it is the only one that you need to know, but this is just rather the information that is just laying some basis for your understanding, so that as you venture into this, you are able to understand the major ideas and major elements of a computer processor. So as you develop your knowledge, you will find this information important. So the address will uniquely identify every location in the memory, and the content will be binary values stored in each location, as you can see. So on the left we have the address, and on the right we have the content in those addresses. So let us now consider two examples of how the MR and MDR register can be used. So when carrying out a read and write operation to and from memory, first let's look at the write operation. So we'll use the memory section shown in the table 2. Suppose we want to read the content of memory location 1110001. The two registers are used as follows. Okay, so the two registers are used as follows. So we have the first register we are talking about is the memory address register. So the memory address register normally stores the address of the memory location that is being currently worked upon. So the read signal is sent to the computer memory. The content of the memory location, the one that we mentioned, this one, are then put into memory data register as it is. Now let us now consider the write operation again. Okay, so we will use the same memory addresses. In this case, we are talking of the we are talking of the memory location where data is found, and also we are talking of the registers. So registers are also just special kind of memories that we use in a computer. So now let us now consider what we call a write operation. Now let us now consider write operation. We'll use the same section again. Suppose we want to show how the value there is a value there in this memory location. The value 10010101 was written on memory location 1111101. So I'm talking about this memory location which has this in it. So we want to look at how was this binary value written inside this memory location represented by this binary value. So the data to be stored is first written into memory data register. So we are assuming that this data is coming from the CPU, coming from the accumulator. So it has to be first written on that memory data register. So this data has to be written into location with the address. So this address is now written into memory address register. So at that moment, the memory on which the information is supposed to be written is already in memory address register. This is the address, and this is what should be written inside that address. So finally, a write signal is sent to the computer memory, and the value this will now be then written into this memory. Okay, so that's how it is. So the data has to be first of all copied into memory data register, then later on with the influence of the signal written in the right memory location for that particular data to be stored. Now we have the system buses, the ones that we talked about earlier. Now let's look at how these buses are. So remember, these buses use parallel transmission ideas. So these are parallel wires which transmit data in form of bits. So there are three common buses, as we mentioned, and these were the buses that were suggested by John von Neumann in his architecture. So we had the address bus, the data bus, and we also have the control bus. Now, the address bus, so as the name suggests, carries the addresses throughout the computer system. So between the CPU and the memory, the address bus is normally unidirectional. So this is so to prevent addresses being taken or ferried back to the CPU, which can be detrimental and feature, and can bring a lot of problems if they find their way back to the CPU. So the width of the bus is very important. So the wider the bus, the more data it can be able to carry or fetch, across the various locations within the CPU and the memory. So if they are wide enough, so then they are able to carry a lot of data. So e.g., a bus of width 16 bits can actually access 2 raised to power 16 memory location, which basically translates to 65,536 memory locations, whereas a bus that has got 32 bits can be able to read this is 4,294,967 8,296 memory location simultaneously. So that is the catch there. So if we have a 16-bit wide address, then it can only be able to locate and fetch data or store data into this number of memory location. But if you have a 32-bit, then it can be able to locate all these memory locations. So it means that you can also be able to store more information in your computer system. So that is it. Then we have the data bus. So data bus is basically but bidirectional. So it can be able to send data from the register to the memory location and from the memory location to the data register. So that is how it is. So the word length, or basically the performance of this data bus is very important. So data bus is bidirectional. This means data can be carried from the CPU to the memory, and also vice versa, and also from input and output devices. So it is important to point out that the data can be an address, an instruction, a numeric value that is being ferried between the memories gadgets, that is the register and the memory location, and where the data is being executed. So let's look at the control bus. Control bus is bidirectional, so it carries signals from the control unit to all other parts of the computer, and it is usually in 8-bit wide. So there's no need for this signal to be, or for this address bus to be bigger than that, because it's primarily used to coordinate the other components of the central processing unit and the computer through sending of signals. So its primary task is basically to send the signal, so it doesn't need to be having a lot of complication in terms of how many bits it should have. 8 bits is already enough. Now let's look at how fetch, decode, execute cycle takes place in a computer. So this how now to carry out some execution and decoding task, the computer, generally the CPU, will do a number of tasks involving the memory location, the address registers that are there within the CPU. So there's a lot of synchrony that has to be there when these things are busy working. So when the computer is busy decoding and executing, there much priority is laid there into making sure that there is high precision synchrony in the whole thing. So fetch, decode, execute to happen, then there's what is supposed to be there. Now let me just take you through how it takes place. There's this diagram here, which I believe it's much way easier to understand, so that you are able to see what normally goes down behind your computer within the central processing unit, so you are able to understand it clearly. So this is how it is starts. So the computer is able to check any instruction. If no, it will go back and check again, is there any instruction? If there is, then yes, it will go to the program counter to check what is there. So program counter contains the address of the memory location of the next instruction, which has to be fetched. This is the address. This address is then copied to memory address register. This is done through address bus. So the copying of the address where data is located from the program counter to memory address registers is done by the address bus. Now the content instruction and the memory address contained in MAR are then copied temporarily into memory data registers. Okay, so this the content instruction of the MR are then copied and placed into the current instruction register. The value of the program counter is increased by 1. Now it points to the next instruction and next data to be fetched. The instruction is finally decoded and then executed, and through and by executing signals, okay, through the control bus to the various components of the computer. So the instruction is finally decoded, executed by the central processing unit, is specifically the control unit, and that is how the execution done. So that's how the execution is done. So it is start by the program from the program counter. The memory address is copied to the memory address register through the address bus. Then address bus are also going to be used to send the signal to the memory location where the data is stored. Then from there the data bus will ferry the content of that identified memory location, the memory location that is in the memory address register. It is the content are ferried from the actual memory location into memory data register. From the memory data register, the content is taken to current instruction register, where the data is subjected to the control unit, and the data is executed there. Then it will be fetched to accumulator, then taken back to memory data register, and finally to a certain memory location where it is found. So that is how the execution is done within the central processing unit. So I believe this is very important for you, as it lays some basis and some basic understanding for you, so that you are able to understand how generally the central processing unit works. So I think that is it for today. We'll link up next time. So if you are watching this video for the first time, please subscribe, and if you already subscribed, please share this video widely with your friends, and let us make and develop this channel, because it is a channel that is geared to helping you understand the technologies that you have been using and the ones that are emerging or trending. So thank you.